evening and good morning. It is our great pleasure to introduce Matthew Mueller, the academic program manager at nTop. It's a pioneer and many company that changed the world of engineering design. And Matthew is not just an engineer and programmer, but also a visionary whose work is transforming how we approach design across the industry. And we may say that from aerospace, maybe to medicine, and TOP's technology are shaping the future. And it simplify and engineering problems. And what is the most important, you today could be a part of this transformation. So, dear Matthew, you're welcome.
Awesome. Thank you so much, Svatoslav. And thank you all for joining. So yeah, as mentioned, I'm the academic program manager at nTop, formerly nTopology. We recently lightweighted our name. And yeah, my goal is to give you an intro to nTop and particularly our education program, specifically for aerospace engineering. So hopefully this is as useful as possible. Feel free to put questions in the chat. Or feel free to unmute yourself and stop me at any point, and hopefully we'll have plenty of time at the end for questions and some live demos. So I'll start just giving us a general overview to nTop, our company, what problems we're solving. Then I'll dive into technology differentiators, kind of look back a little bit at the state of the art for the CAD industry today. Dive into some of our use cases. We'll go through conceptual design, multidisciplinary analysis and optimization and inverse design, then honing in on detailed design, talk about our flow analysis capabilities, and end by talking about our integrations, how we fit into the broader spectrum of other CAD tools and other computer-aided engineering tools. And again, lots of time for questions. So who are we and what problems do we solve? So in general, we're seeing that the aerospace industry is being pressured to innovate faster at the same time as the requirements for their designs are getting stricter and more intense. And from an education perspective, students need to keep up to be able to get these jobs and join industry immediately. What we're hearing from customers is programs that used to be 5+ years are being condensed into 18 months. And we're seeing a similar trend across the industry. I picked out a couple of recent quotes just about the high stakes aerospace and defense environment and how speed is really imperative, especially with increasing amounts of competition and fast changing needs, as you very well know, in Ukraine. And of course, technology is changing this. There's new AI technologies, modernizing systems that are helping to drive this accelerating pace of change. And kind of one of the main issues that nTop is seeing is that the traditional method of requirements to design is too slow. When you come up with your initial design, each evaluation you do is typically a serial process, which is very manual, takes a lot of work. Anytime you generate your new CAD with new parameters, it's a very manual process. And oftentimes, as you change those parameters, the CAD fails to update. Your fillet breaks the number of edges, and you need to reconfigure your design intent through your parametric features. And it is just a very time-intensive process. Then traditional simulation is very expensive, both computationally expensive and just in terms of the amount of time it takes. And it's all a very long, arduous process. So that's kind of one of the key things that nTop is trying to solve in the industry. And the two key bottlenecks that we've identified in terms of design challenges, particularly for advanced aircraft design, is geometry and simulation. So as I mentioned, traditional parametric updates are slow and often break your geometry, causing you to go back, and your automation process just can't run efficiently if you're spending so much time breaking broken geometry. And then, of course, with simulation, each time you make that geometry update, it's a very arduous process preparing the geometry for analysis, meshing, making sure all of the parts of your geometry are correctly labeled and differentiated. So our goal is to help make higher fidelity models for both geometry and simulation, and do them in a more robust way and faster. So who is nTop? We were founded about 10 years ago, and our goal is to remove barriers to optimization, lower the cost of revision, and increase the speed of your iterations. So you can see on the bottom are logos of just some of our customers, but you can see that the aerospace industry is definitely one of our key industries here. So all of the aerospace primes in the US are nTop customers, and we're constantly working to increase their usage and help them leverage nTop across their design cycles. So generally, we're used for highly engineered designs where iteration is key. And we fit from conceptual design at the earliest stages all the way through to detailed design, topology optimization. And we're really meant to complement existing or traditional CAD and CAE systems. We're not going to replace all of your tools and be your full end-to-end solution, but we really augment your capabilities across your design space. In terms of the education mission, we have thousands of monthly active users that are using our free education license. And it's a good question. Why do we give away free licenses for education users? Kind of two of our main goals here. One is to pay it forward. It's the right thing to do. We want to help the next generation of students and researchers learn with the best tools that are out there, the most modern, advanced engineering software tools. So that's why we want to give it away for free. But it also helps with application discovery. A lot of our corporate clients are too busy or bogged down in too many mission or business critical requirements to explore the out-of-the-box application. So we've seen a lot of really exciting stuff coming out of academia that helps us make a better product and helps our customers understand what they can do with nTop. Of course, this also cultivates that kind of business pipeline for us. We want students to go into industry and bring these skills using nTop and say, you should buy more licenses to nTop. But really, we want to pay it forward and help accelerate application discovery. So as mentioned, we provide free academic licenses. You could go to ntop.com/education, fill out the form. We process the license requests every day, Monday to Friday. Then we also have a full learning website, learn.ntop.com, with self-paced courses that you can take. We have support.ntop.com with lots of knowledge articles, frequently asked questions to help you get started. And then we also have a Discord server for our education community with over 1,000 members and growing strong every week, where the community engages with each other, shares cool updates, research, but also asks questions and gets help there. So that's nTop. Now let's dive a little bit into our technology, and specifically focus on implicit modeling and computational design. So we kind of have three main pillars of our technology differentiators. Implicit modeling, which is a kind of new approach to creating geometry that's different from traditional boundary representation, which is kind of the status quo for traditional CAD. It provides fast and reliable modeling, and you can use these flexible field-driven parameterizations to create your geometry. And importantly, it leverages modern compute hardware. So traditional CAD is locked to the CPU, which is a serial, computationally expensive, slow process, but implicit modeling really leverages the GPU in multiprocessing. Similarly, with accelerated compute, we're leveraging that GPU technology. We're implementing GPU native algorithms. So one example, we just released about a month or two ago, a lattice-Boltzmann method solver for CFD, which leverages the GPU. So it's much faster than traditional CFD methods. And this really provides a scalable design space exploration and allows you to generate lots of data quickly for AI and ML training. And related to that machine learning, we're really invested heavily and fit very well within the machine learning story. So physics acceleration, physics-informed neural networks, real-time predictions, and importantly, our implicit modeling is differentiable. So for inverse design, it makes it much easier for optimization algorithms to find that optimal design space for and converge. So let's take a look back a little bit at the CAD industry and why implicit modeling is so revolutionary and important today. So from 1970s, when the initial CAD ideas came out of MIT, little has changed. They've evolved, and we've gotten to kind of the traditional parametric feature-based CAD systems that we know and love today. And it's constantly evolving and growing, but it's pretty similar core technology to what we had in the 70s. And some of the key weaknesses, one is that it's fragile and unreliable. So as I mentioned, if your fillet intersects and the number of edges changes, if your fillet's too big, you typically need to do some manual intervention to solve that, which is, if you're trying to do a design of experiments, a very manual, tedious process. The data itself is very big and poor scalability. So each edge needs a precise definition. Each surface needs a precise definition. So there's NURBs everywhere. And as I mentioned, it's just kind of based on old compute hardware and slow. It's not GPU friendly to have to compute every individual edge and face of geometry. Implicit modeling, on the other hand, is creating geometry just with mathematical equations. There's no fragile calculations that you need to do. Your topological modifications just work with the math. The data size is very small because we're using a concept of signed distance fields to actually define your geometry. So rather than defining your edges and faces, we just evaluate your mathematical expression at x, y, z. If the value is negative, that's geometry. If it's positive, that's not geometry. But those fields can be flexibly used in many other ways. So it's a very scalable and efficient way of defining our geometry. I think when I go and do a demo, the signed distance fields resonate a little bit better. But that's kind of the core of implicit modeling. And again, it works on GPUs, so works in parallel kind of applications. So really accelerates the iterations and your engineering design workflow. Especially when it comes to things like Boolean unions, it's very efficient to do that mathematically rather than calculate all of your new edges and surfaces as a traditional CAD system does. So you could see that example in the top right here, implicit model with a signed distance field. You can intersect these two equations just using a simple max function and define where your solid geometry is. So why do we need something new? What's parts of these kind of industry-wide transformations that's driving this need? The first is digital manufacture. So additive manufacturing technologies come a long way, which makes complex parts much more desired. It's easier to manufacture very complex parts. So as your part complexity grows, as your lattices get more complicated, it's hard to scale that on traditional CAD systems, which means more chance for geometry errors, more scalability problems. This also allows us to manufacture with non-uniform materials with either lattice infills or multi-material type applications. And BREP alone is not sufficient for defining those types of non-uniform material properties. Computational design and just the algorithms on how we are designing are always improving, and it's program-driven, not human-driven. So we can now encode your conceptual models with your implicit modeling technology. And again, back to that computing hardware, we've come a long way since the CPUs of the 1980s, and implicit modeling is really the way to leverage that. So this computational design process that nTop is really championing starts with building that computational model where you're starting with that requirements-driven process. It could be simple, metrics for your requirements, or it could be physics-driven calculations that are driving your requirements. And that's what can be built into your computational model. So that analysis is really baked into both the geometry generation and the analysis of it. Then using our implicit modeling technology, it's very easy to do this iteration quickly and robustly. We like to say that implicit models are indestructible geometry because the Booleans and the way that the geometry works is really robust. And then ultimately you can converge on that optimal design before you then integrate with other CAD, CAM, CAE systems to finalize and make your product. So diving into our first real use case for aerospace engineering in particular is conceptual design. Maybe I'll come up for air quickly, look in the chat. Any questions or anything so far? Yes, Vadim.
Yeah, Matthew, I have a question regarding implicit modeling. So can you just explain? You mentioned that you defined the mathematical equations that not actually defining the border, but defining the field where the geometry is inside. But what about the complex boundaries? Do you still use splines or other ways to define this geometry? What is the process of that? Can you comment on that?
Yeah, so the edge of your implicit model is the zero plane of your signed distance field. So this is maybe a reason to just quickly come in and introduce nTop, the product. So this is what an nTop notebook looks like when you start a new model. So you can add a primitive. So I'll add a box and I'll add a sphere. One of our favorite models is the sphere cube. So here we can click on the box. We can click on F, which is your field viewer. Then I can turn off the visibility. And here we can see the signed distance field that box generates. And inside of the box is your negative, and outside of the box is positive. So it's that zero plane which defines your geometry. You can, so just to go a little bit further here, maybe I'll do a Boolean union and put these two bodies together. And maybe I'll add a blend radius there. A blend radii are very powerful. And here you can see we now have an updated signed distance field, which if I hide this again, that zero plane of our signed distance field is what defines our geometry. You can use splines and various curves to help define your geometry. And those splines are driven by their equations. But if you're creating just an implicit body, we don't necessarily have a curve that defines the intersection of where this fillet radius changes, if that makes sense. At the end, I'll talk about how you can then convert your implicit body to a BREP body for integration with your CAD systems. But that is sometimes one of the difficult parts, is going from an implicit body to a CAD body.
Yeah, Matthews, thank you. This makes sense. Yeah, thanks.
Of course. And I'll come back and do some more demos later on. Any other questions before I keep going? Okay, I'll take silence as a good sign. So conceptual design is one of the main use cases that nTop is really targeting now for many reasons. One is because the further in your design process you go before you realize that you're not actually going on an optimal design path, the greater the costs of revision. So if we can help companies and product designers converge on that optimal solution as early as possible in their conceptual design phase, we can help save a lot of money for revisions down the road as they've gotten farther along in their detailed design process. So the idea is you can build your computational model in nTop starting with your requirements. You can do your, as I said, physics-driven requirements for an aircraft, your mission profile, your weight estimations. You can do your space requirements, holdouts, so that all of your components fit, and let that drive the geometry around it, for example. And if you parameterize that model in the right way, your implicit geometry will be very robust as you make these updates. So as I mentioned, things like blends just come for free with implicit models, and you don't have to worry about something breaking at the edge of some parameter range that you're exploring. So it is very robust geometry that we're leveraging here. And you can tie that analysis very closely into the loop. So it can be just simple physics equations that you're using for your analysis, your lift to drag ratio based on your wetted surface area, or you can do your CFD or your stress analysis directly in the loop there. The meshing process can all be part of that computational model. And as you explore your design space, you can then close out your design on that optimal before you've gone into detailed design, before you've wasted time going down the wrong non-optimal path. So this is one of the really powerful use cases for nTop that we are promoting heavily, especially in the aircraft design space. Just a few examples of how parametrically robust our implicit models can be. This parameterized Blisk, you can see no other CAD system. You can see these updates in real time as you're dragging a slider. And I can demo this file later, but as you can see, all of these parameters using our GPU acceleration, you can see the updates in real time. They're super robust. So you could do that design space exploration in an automated way without worrying your geometry is going to break at some point. Similarly, with fuselages for aircrafts, you can use these equation-driven methods and parameterization techniques to explore all of your design space early on to make sure that you're choosing the optimal design before you get into the detail parts.
Matthew,
Yes.
may I ask you, so when I make some transformation due to the sliding, what main characteristics are taken into account? For example, it could be aerodynamic, it could be in a strength, or it will be in a combination of both of them. So how I may determine what I need for transformation as a key parameter?
Yeah, so it all depends on how you set up your model. These are the parameters that control the geometry, but your analysis and your requirements that are driving your design can be baked into it in any number of ways. So you can write your equations in the notebook on the left. So one thing I like to say is, don't think of the notebook on the left like a parametric feature tree, as you would see in a traditional CAD system. Think of it like a Python notebook, like a Jupyter notebook. You can have all of your equations baked in here, and it's a functional programming language. So you can refer and use different aspects of your notebook at any point above or below. The order doesn't matter. So if you have your lift to drag nominal equation encoded in your notebook, you can use that to drive the ratio of your wingspan to your fuselage blend. I'm making stuff up. I'm not an aerospace engineer, but
Mhm.
that's an example of how you can build in that kind of nominal physics-driven analysis into your notebook. Of
Okay.
course, you can also run stress analyses, flow analyses on your geometry. And then in terms of kind of closing the loop and doing that optimization, that's a very specific kind of problem and depends on your specifics. We're actively working on integrating more optimization algorithms into nTop. So you'll be able to do all of those types of workflows directly in your notebook. Currently, we have field-driven optimization or topology optimization that are built in, but we're moving towards more multidisciplinary optimization type problems where you have that trade-off between stress and lift, for example. So
I see.
these examples are really just showing the kind of robustness of our implicit modeling technology. So with a full, A320-like model, you can see how easy it is to explore all of these different shapes using that field-driven modeling capabilities.
Okay, thank you.
Yeah, Vadim?
Yeah, Matthew, if I understand correctly, this means that those sliders are user-defined, right? So user can create these sliders for their model, and in that case, what computational engine is in use? So do you have API for Python, or I have to define all these equations inside the nTop?
Yeah, great question. So the parameters are defined in your notebook. So you need to, come up with your own mathematical equations to define the geometry. We're working on other ways, other interfaces that are more computational for generating the notebooks themselves. But as of today, you have to define that in the notebook. Once you have your notebook defined, however, we have a command line interface that allows you to iterate over your design process and generate lots of data very quickly as you do your optimization. So that command line interface, you can run it through Python or MATLAB or any scripting environment. We have a Linux option for that as well, where you can specify your inputs, and then whatever the notebook does, you use as an output. So that allows you to do your design of experiments and really explore that design space and converge on an optimal design. But yes, today the user defines the geometry and the inputs and the parameterization of that geometry in the notebook itself.
So your notebook is supporting some kind of programming language, right? So I can write these equations in the programming style.
Yes, so that's kind of the application itself. We don't currently expose the access to the modeling kernel at that lower level. So it's that kind of block-based interface is the UI.
Okay, I see.
Yes. Again, we're exploring ways of doing that, but that's a longer term.
Yeah, I understand. Thank you.
Cool. So that's the conceptual design application, and really what we see is driving a lot of value for our aerospace and defense customers to make sure that they have a better probability of winning the contracts in the first place, and then have a more optimal design as early in the process as possible to drive a lot of that value. So yeah, this is maybe Vadim going into your question, focusing on then the multidisciplinary analysis and optimization and inverse design applications. And nTop Automate is that product, the command line interface. So again, back to that kind of initial problem I mentioned, that requirements to design is too slow. It's highly manual, traditional simulations are expensive, CAD is not very robust, and each evaluation is serial. So the proposed methodology that nTop is promoting is inverse design. So rather than having just a loop like that, the first step is to create your model, and then you create your geometry model, and then you can train a physics surrogate model using your nTop model. So Cloud Fluid is our kind of core CFD technology in nTop. And what you can do is run your design of experiments, generate lots of CFD data across your specific design space to generate an ML model. And then you can use that surrogate physics model to do your inverse design, to do your optimization based on specified constraints and optimization goals. So you can very quickly converge on that best design. And this is a much more robust method than other generic physics-informed neural networks, because the machine learning model is trained on your specific design space. Your specific parameters of interest is what is being used as input data for your machine learning model. So for an aircraft, for example, there are some examples out there of just kind of generic AI trained physics models for external aerodynamics of an aircraft, but you don't know, it's almost definitely not trained on the specific configuration of an aircraft that you are designing. So you can use your nTop model to generate the data across that design space so that you can do that inverse design and know that your results are trained specifically on your design space. So as I mentioned, we have this nTop automate interface that allows you to do that multidisciplinary optimization, your design of experiments, and you can programmatically execute that nTop model from any coding interface, including Linux. So nTop, the UI only opens on PCs with the right GPU and system requirements, but the nTop command line interface you can open from Linux. So those inputs you specify as kind of just a JSON input, and then you can run your DOE using Python or any specific kind of model MDO tool like Model Center, Mode Frontier, to generate your data and understand that Pareto front of your optimal design. So on each execution, your notebook is run, and whatever you specify as that output, your key parameters of your analysis, of your nominal physics equations, of your geometry itself, you can use as input data for that inverse design problem. As mentioned, we're heavily investing and exploring the AI accelerated conceptual design path. So once you have your model design space built in nTop, you could do that design of experiments and use it to train your AI ML model. So we've been collaborating with NVIDIA on this and been able to quantify the value of their approaches and quantify the fidelity of their approaches. So you could see with nTop and Luminary Cloud, which is one of our partners that does computational fluid dynamics for external aero, each simulation run takes hours. But if we generate lots of data across our design space in an automated way that's very robust, and then use NVIDIA to train that physics informed network, each analysis goes from hours to minutes. And you can see there's a less than 5% delta comparing the full physics CFD to the AI informed CFD, showing that the fidelity of these models is robust and reliable because it was trained on your specific design space. As mentioned, we have API integrations that allow you to automate this in lots of different ways. And then this is an early kind of demo, but shows what that kind of inverse design approach could look like if you plug your trained neural network back into an nTop notebook. So in each of these cases, here we're trying to do an inverse design and maximize the lift of our parameterized aircraft. And we can see the geometry that's generated as well as the predictions for the CFD based from that neural network. So it's very quick. You could see for minimizing drag, that new configuration, and each of these optimization algorithms are being generated on that neural network trained with data from nTop. So again, this is not, I mean, you can do this today, but it's a very involved process. We're working on making this more of a plug and play kind of thing. So it's easier for any customer to implement themselves. So that's how you use your conceptual model for multidisciplinary optimization, inverse design. But nTop is also great for detailed design. So design for additive manufacturing, topology optimization, latticing, field-driven design. That's kind of our core customer base today, actually. The conceptual design and MDO use cases are newer applications of nTop that we're really pursuing, but it's also really good at detailed design. So this is a Type 1 UAV that Brad, our CEO, has designed entirely in nTop. So typically, because we don't have the types of splines and specific referenceable surfaces that are required for detailed design and engineering drawings, users don't go into this level of detail on their design. But because this was entirely 3D printed, we didn't need an engineering drawing. We could do the full detailed design all in nTop. So he took this concept that was optimized in nTop and then broke it down into a full 3D printable design down to every little component, including a little spring latch that closes down on the electronics bay. So you can do this level of detailed design in nTop as well, although it gets increasingly complicated for this type of parametric design. The more typical use case that we see is something like topology optimization. So you can define your boundary conditions directly in nTop. So these are all native blocks in nTop. I see some questions came in on the chat, so I'm just going to take a second. Can I use my recent CAD model? So yes, you are able to import CAD models into nTop. You can convert those CAD models into implicit bodies and do your topology optimization on those imported models. You can, I'm not exactly sure what the time savings would be. Obviously, the topology optimization algorithm leverages your system spec. So the more RAM you have, the better the performance will be. But I will say that our topology optimization interface and algorithms are first rate and as good as it gets. And I'll show you soon the way that you could use the data that nTop has for field-driven design is an extra powerful part of implicit modeling that we don't see any of our competitors really having. So once you define your boundary conditions, you can also define your payload positions. So this is a very simple nominal example, but you can have your kind of holdouts for avionics or fuel or any other systems you need in your aircraft. You can break down your design into discrete sections. So it can be printed, for example. And then you can go in and do your topology optimization on each of these segments using those payload requirements as inputs to make sure that, or as constraints for your topology optimization to make sure everything fits as you want it to. So that's a perfect example of how you might leverage a CAD model for input to your topology optimization in nTop. So a workflow might be you do your conceptual design in nTop, converge on your optimal outer mold line for your aircraft. Then you go into CAD, do some of your detailed design based on that optimal outer mold line. And then you come back to nTop to do your topology optimization, kind of your final detailed design from your CAD parts. Of course, you can do your stress analysis directly on your topology optimization solution to see the stress concentrations and understand whether it fits your requirements as set up. And then here's the field-driven design part. You could actually use the outputs of your stress analysis to specify some other field-driven parameters in your design. So in this case, we're specifying a multi-material model based on the results of our stress analysis. So at the higher stress locations, we're going to specify a stronger material, and at the lower stress locations, we're going to specify a lighter weight or cheaper material, for example. And we're using the field of that simulation result to drive this multi-material placement. So you can see even on the inner parts of our geometry, we have those materials defined. So for multi-material 3D printing application, this is ready to go. So super powerful using the outputs of your simulation results as the fields that drive your geometry. You could do that same thing with your shell and infill structure. So nTop is really good at generating lattices because that implicit geometry is very efficient. So if you wanted to generate this type of lattice in a BREP CAD system, good luck. But nTop does it very efficiently. And you can, again, drive the shell and infill structures with your field results or run an optimization algorithm specifically on that field to optimize for your constraints and requirements. So you can see here, we ran the shell and infill field optimization to make sure that the thickness of the lattice on the inside is optimized for our specific constraints and goals for the design. So in this case, we're optimizing the infill thickness based on those simulation results. Sorry, I saw another question come in. Does nTop have 3D printing software, which I can set parameters for my 3D printer like Ultimate Cura? So we have integrations with 3D printing partners. Ultimaker Cura is not one of them, but you can use the parameters of your 3D printer, like your extruder nozzle diameter, your layer height, for example, to drive constraints or requirements of your topology optimization algorithm or your field optimization algorithm, or even just your thickness of your lattice that you're generating. So you can parameterize it yourself and do it efficiently, but we don't necessarily have a direct integration with a CAM provider. You can do some slicing capabilities in nTop to analyze your design and make sure that it is optimized for a specific 3D printer, but then the toolpath generation will have to happen separately. And at the end, I'll show one quick example of 3D printer, a CAM software that we've partnered with and directly takes our implicit models from nTop. So in terms of native flow analysis, again, we have stress analysis, modal analysis, buckling, basic thermal analysis, but I also wanted to highlight our native flow analysis. So this is a lattice Boltzmann method solver, which runs on your GPU, so allows you to really efficiently get some results for your designs. So again, the goal is to very quickly get to your results with just your implicit model. So you don't need to mesh your full model. The lattice Boltzmann method discretizes the flow domain into voxels, which allows it to run very efficiently on your GPU hardware. Now this is kind of a mesoscale analysis, so it's not necessarily as accurate as a full CFD particle solver, but it is orders of magnitude quicker with similar fidelity results. I'll say currently it is not tuned for external compressible flow aerodynamics, even though that's the example we're showing here. That's on the roadmap and hopefully should be shipped in the next 2 to 3 months. But currently it's really meant for internal flow, but we're constantly expanding the capabilities and tuning it for new domains. This is an example of a full Bliskin stator model that has nTop fluids analysis through it. So you can see kind of the level of complexity that it's able to handle and how powerful it really is. You can see heat exchangers are kind of one of our bread and butter use cases because we're very good at generating these highly complex lattice structures. Then now we have native flow analysis capabilities. So you can do that full closed loop optimization all just with an nTop notebook. You can generate your input designs, run your flow analysis, and optimize for pressure drop or average velocity or anything for your heat exchanger to make sure it meets your use case. And again, this is showing external flow as kind of a demonstration, even though today it is not tuned for external flow, but shows how efficient it is for doing your kind of design of experiments analysis all directly in nTop. And so in terms of integration, so you have your implicit model, your concept of outer mold line for an aircraft. How do you then go back to CAD? How do you manufacture or analyze it using ANSYS, Fluent, or some other system? So we do have the ability to convert your implicit body to a CAD NURB surface for then integration into a traditional VREF CAD system. Or, of course, we have lots of meshing capabilities, so you can kick the design out to ANSYS, Fluent, or any other simulation platform for analysis. So pretty much all of our surfaces are G2 continuous, so very smooth surfaces. At some extraordinary points, there is some G1 continuity. And we're very proud of our meshing algorithms and are always improving upon them to make sure they're watertight and clean and really efficient for the use case. So in terms of exporting to NX, a lot of our aerospace customers use NX, but it's similar processes for CATIA or SolidWorks or any other traditional CAD system. But you can see how you're exporting those NURB surfaces, importing them into NX to check your surfaces. If you're then doing your detailed design, maybe you need to reference these surfaces for regenerating your model for the detailed design. But you can see for things like shelling, nTop is very good at that and useful for things like composites layup. Oops. Yes. So in terms of zebra line checking, you could see how smooth the zebra lines are of the NURB surface. We actually just in the latest release of nTop have native zebra line and metallic surface checking. So you can do that basic surface checking in nTop, but of course it's also important to make sure the NURB surface we're generating is continuous as well. And you can do all that slope analysis as well. I think one of the important things to highlight is doing your automatic domain segmentation. So one of the key use cases here that I've come across is users are designing a heat exchanger in nTop and then want to use ANSYS Fluent for analysis. So you can define your domains for your cold fluid, for your hot fluid, for your metal interface, all in nTop, so that when you're exporting the mesh, it's smart enough. It has that metadata to know the domain segmentation. And importantly, the domain segmentation is parameterized in nTop. So as you update your geometry very robustly, quickly, the domain segmentation also comes along with that for free. So the downstream simulation platform also knows, in this case, where the wing surfaces are, where the tail surfaces are. So you can do that analysis automated. You don't have to reset up the simulation every time. And last, I'll just quickly mention this partnership with Materialize Magics. So you can directly import your implicit model, your .implicit model from nTop. You don't have to do that meshing or convergence, converting to a CAD body beforehand. And more partners are adding support for our implicit modeling geometry. So Fusion 360 just added support. You could directly import a .implicit model from nTop without doing any conversions. And SimScale is a cloud simulation platform that just added support for implicits for conjugate heat transfer. So we're constantly expanding our kind of network of partners that are leveraging the power of our implicit models. And so that's what I have in terms of slides. Hopefully I answered at least most of the high-level questions about what nTop is and where we add value and what problems we solve. But I'm happy to answer any additional specific questions or go into nTop and do some more demos to help make sure that everything makes sense.
Okay, many thanks, dear Matthew. It was really interesting, and it's a good, wide horizon for new techniques for designing, for the understanding the nature of things completely within a small involvement of the forces for the calculation. And maybe, first of all, is a question. And top looks like the good solution for simplifying and modification of some geometry, some design. But I guess you need to know the basic principle of the design. It's my point of view because you must understand the nature of your object. According to that, how do you think, compared to the already existing CAD, for example, ANSYS analysis and so on, how it will be good to blend it, maybe for comparative analysis or verification, maybe some integration of both original and nTop process. I mean, from the point of view of verification. So I have good results from nTop. So what is my next step? Could I prove totally to it, or I need some verification? If I should verify, how I should verify it? Could I use an other approach of nTop to prove it? Some
Yeah, so a lot there. I think in terms of verifying the kind of analysis results, we publish white papers on our specific stress analysis algorithms to show benchmarking against kind of accepted results, and same with the flow analysis. But yes, you definitely should do your own kind of validation to make sure that the results from nTop fit. And again, we have a lot of different documentation about integrations with ANSYS or other simulation platforms, so that to make sure you're able to do that type of analysis. Or if you just want to use an external tool like ANSYS for your analysis, you can do all of that automated through the command line as well. So again, that kind of domain segmentation allows you to use nTop for your geometry generation and plug it in to an external solver if you have already done your validation on that external solver. Does that answer your question?
Yeah, yeah. So also we have some questions in chat.
Yes.
What is the hardest problem you face in while development nTop?
Yeah, it's a good question. I think it's always just trying to balance the needs of customers and trying to get the highest value. We're still a pretty small company, so we want to make sure that the features we're adding are really driving as much value as possible for the customers. But there's a lot of very technical problems that take a long time to solve, like adaptive meshing is a project that's taken a long time and is very close to now being shipped, where on a part like this, you don't need a very dense mesh just on the side of a cube face because it's pretty simple geometry there. But at this fillet, then you want some pretty refined meshes to make sure you're capturing any complexity there. So that type of technical problem takes years to understand the fundamental research of generating triangle meshes and then optimizing that algorithm to make sure it runs as efficiently as possible on all types of hardware. But, yeah.
And if we talk about the customers, the nTop will be friendly for users who knows what kind of product. For example, SolidWorks, I don't know, Siemens NX, something else.
Yeah,
What
so
is the basis for?
that's an interesting question because nTop is different than
Yeah.
traditional parametric CAD, right? Here, maybe I'll just do a simple lattice example. So here, oopsies, that I want to do a rectangular volume lattice. And here I'm going to use my implicit body. I'm going to use, let's say, a gyroid unit cell. I'll specify my cell size. So here's now my gyroid. I can change my unit cell size, see that update. But this implicit body is still here. I can still do anything I want with it. In a traditional CAD platform, once you've consumed a feature downstream, you can't always reference in the same way. So it's a functional programming language. So there are some just kind of fundamentally different concepts that you have to get your mind around. And that's been an interesting process for me to go through. But you could see the fields here that are driving the geometry of the lattice. And that allows you to do very flexible and interesting things. So here is an example of a heat exchanger. And you can see that we're not just showing the flow analysis, but we're actually using the flow analysis to change the density, the thickness of the lattice across the channel to optimize it for pressure drop, for example. So we're doing two flow analyses. We do a first flow analysis here on just the empty channel, and then we use the results of that flow analysis to drive the thickness. So we use the pressure field from this flow analysis to drive the thickness of the lattice across the channel. So to answer your question, it is its own thing. There are obviously transferable skills if you understand 3D parametric CAD, but the way that you model is quite different in nTop compared to parametric CAD. One example here is this very simple aircraft. So if I want to change the dihedral, again, you see that performance. You can't get that in any other CAD. And it's not only the dihedral, it's the blends that come along with it. That's something that's really difficult to get tuned and robust in a traditional CAD platform. But the way that we're generating these wings is not with a loft or a sweep of an airfoil along a guide curve. We have to use fields, these implicit fields, to generate the geometry. So one thing I'll highlight here is our use of custom blocks, as we call them. So you can kind of package up an nTop notebook and use it as a single block in another notebook. So this allows you to reuse workflows. So in this case, we have a workflow for generating a single panel wing. We can package that up into a custom block and then use it in designs very easily rather than regenerating that full workflow. So here we can come in and look at the custom block here for how we're generating the wing. You can see we have a bunch of inputs here, and that's similar for our nTop Automate. You can very easily run a design of experiments on this, for example. And we have nested custom blocks. You can see we have a NACA airfoil generator block as well. It's a custom block. But to generate this airfoil, as I said, we're not just mapping, we're not just sweeping or lofting along a plane. We have to generate this two-body field. So let me hide the wing. So based on just an input leading edge and trailing edge, so this is our bounding box for our wing, what we have to do is make this field that scales proportionally. And you could do this with two plane wings and add twists and all of that, but you have to think about the geometry differently. You have to think about it in terms of fields. So once we have this field, we use the concept of a remap block to take our airfoil. So here's our airfoil. And then we essentially Boolean that with the remapped field to generate the planar wings. So it is a very different approach to creating geometry. To do a very simple example of that remap. So here we have our basic sphere cube. If I want to remap this, I'll start with just putting X, Y, and Z in and isolating it. So these visibility things. But rather than just doing X, Y, and Z, I can multiply Y by 2 and see that it squishes all of the Y dimensions from the original sphere cube into the Y times 2 field. So it's a little bit counterintuitive that if you do a smaller number, if you multiply by a smaller number, you're going to expand, but you're mapping the Y coordinates from that initial space into the Y divided by 2 space. So that's how you expand it. So all of that is to say, you have to think about geometry a little bit differently. But once you get there, you can see the power that it offers. So here's that parametric blisk that I showed before. And you can see in no other CAD system can you just slide something and have it parametrically update. So quick and robust. And similarly, we've discretized the number of mounting holes here will always be an integer and be properly spaced based on that inner diameter. But it's all very robust. And this is all parameterized based on a research paper that one of our product engineers found. So theoretically, you can plug in the physics equations for blisk design, and that can drive the curvature at the root or at the tip. And all of that can be your requirements-driven computational model.
I see. And there is another question. Does nTop have 3D printing software with which I can set parameters for my 3D printer like Ultimate Cora?
Yeah, so I think I mentioned for that, we don't have our own 3D printing software. We do have some slicing capabilities, so you can optimize your design for your specific printer, your nozzle diameter, your layer height, and do your slicing in nTop to make sure it will work. But ultimately, you will need to do that CAM toolpath generation in another slicing software. We have all of the meshing blocks. Mesh from implicit body is our kind of most basic one, where you can just generate your mesh and export it. Yeah. I see a question. Do you have any concurrence in your field? I'm not quite sure I understand that question. So if you want to unmute and...
The other company that performs the same things.
Gotcha. So there are a couple of other examples of implicit modeling. Altair Inspire is one of them, one of our kind of main competitors, but their technology is, from my understanding, I don't pretend to be an expert on their technology, but from what I understand, they don't allow you to control implicits in the same way as nTop. So the types of fields that we are able to generate are really fundamental implicit modeling. And that's where we're really pioneering the ability to generate geometry. But there are some other examples in the industry of similar implicit modeling. I see, can I run nTop on my laptop with no GPU? Unfortunately, we do require a GPU. I can send the system requirements guide, or if you just Google nTop system requirements, you should be able to see our system requirements guide. If you don't have a NVIDIA GPU, but some other GPU, sometimes you can do some basic modeling, but officially we don't support that type of hardware. For our flow analysis, you definitely do need an NVIDIA GPU. That is all that nTop runs on.
Okay, so, and it was a question about the demo of example of, I think these things. Do you have a set of demos that we may use for familiarization?
So we have a full learning center. So learn.ntop.com has a lot of examples there. Support.ntop.com has also a lot of examples. All of our training guides and example workflows provides a sample file typically that you can download and use for any purpose. So for example, we just at the end of last week wrote a training guide on how to create these two body fields to generate a wing, for example. Another question about IP issues with ntop.org. Yes, so that is something that we always have to deal with. nTop is also the name of a networking diagnostic tool. We're ntop.com, they're ntop.org. And that was part of the issue with lightweighting our name from nTopology to nTop. So no, we don't have any IP issues. We do have an agreement with them, so we could use the name because they did exist first. But nTop is our product name, and I think just has more of a ring to it. So, but officially we're still nTopology, I think, is our registered company name. But in terms of example files, I'll also just mention from our home screen. So anytime you open nTop, we have a bunch of examples here that show examples for topology optimization, for example, or design of experiments, heat exchangers, field-driven lattices, all that kind of stuff. So these are often a good place to start, but if there's specific example files that you're looking for, that's where I come in. I'm here to help you succeed. So if you want to bring nTop into your classroom, that's what I'm here for, to help you succeed, help generate example workflows, can even help with curriculum development. Happy to explore workshop opportunities so we can get lots of students up to speed quickly, and leveraging nTop for conceptual design or any other use case. I see another question. Can I put a one figure into another without fillet? So yes, you could do your Boolean union. So I'll just really quick recreate that sphere cube example. Oopsies. And if we do a Boolean union here, we can specify a blend radius of 0, and that will be a sharp corner here. And if I look at the field of this part, you can see that it is a sharp corner. But you can specify different types of blend radiuses. And again, that's one of the powers of nTop, is that very robust ability to do your unions with a fillet. So maybe quickly, big one. If I turn on our analysis, you can see our new curvature analysis. We have metallic, or we have zebra stripes. You can see kind of the smoothness of our surface, which for real aircraft design companies they spend so much time making sure that their surface is as smooth as possible, and hire engineers just to do that type of curvature analysis. See a question: does your explicit feature ready to get model optimizing from a list of conditions that sets different values of load for model, while aerodynamic performance on high speed and player ML finding better solution? Did I understand that right? I'm not sure if I fully understand the question, but I think what you're asking about is multidisciplinary optimization. So if you set up your computational model, your nTop notebook, such that you're able to export the different outcomes of your analysis. So for aerodynamic performance, for example, you could theoretically use nTop fluids. Again, our solver is not currently tuned for external compressible flow, but once it is, you can do that design of experiments to analyze your aerodynamic performance. For example, you could say your pressure difference on the leading and trailing edge, or something like that. You can generate a machine learning model with those findings to be able to more quickly do your analysis and converge on an optimal solution using your inverse design approach. I'm not quite sure I answered that question, but feel free to unmute or write in the chat if you.
Okay, thank you. I
Yep.
get all information. I think that's the answer that I asked.
Okay, cool, great. I'll maybe quickly mention we're actually sponsoring a hackathon with the American Society for Mechanical Engineers. That's about a heat exchanger design, and it's all about exactly that process of taking a simulation results over a number of parameters, training a machine learning model to be able to do your inverse design and come up with an optimal set of input parameters. So in this case, our input parameters are lattice cell size in the X and Y dimensions, as well as inlet velocity. And you can see this is our flow analysis it's currently solving. You can get a sense for how long it takes. Obviously, sharing my screen on Zoom takes a little bit of my GPU, so it's not quite as quick as it would be otherwise. But then once my flow analysis solves, I'm able to extract the mass properties, the surface area, or the mass of the part. But then I'm also able to extract the outlet pressure, inlet pressure, calculate the pressure drop from inlet to outlet. So that's a key requirement for a lot of heat exchanger designs. And then I'm also able to evaluate the time average velocity across the whole domain. So Lockheed Martin, one of our customers who we've worked on with a similar problem space, wants to make sure that the Reynolds number for the flow inside of a heat exchanger is high enough to make sure that there's enough turbulence to optimize their heat transfer. So based on all of these outputs, your mass properties, your pressure drop, and your average velocity, you can do that design of experiments. You can iterate over a number of different lattice cell sizes, different inlet velocities, and try to converge on an optimal design given a set of constraints and optimization goals. So in our case, the mass has to be below a certain weight, pressure drop has to be below a certain value, and internal velocity needs to be above a certain value. And then you're optimizing for surface area. You want most contact between the hot and the cold surface to get the most heat transfer as possible. So by training that machine learning algorithm, they can then do the inverse design to optimize it. And all of that is automated with a simple Python script. So this is the script for generating all of the geometry. It's just nested for loops to run that notebook and then take the output of those simulation results. So it took me, I don't know, 4 or 5 hours to run through these 125 design cases. But then once you train the machine learning model, it should be very quick to get your optimal design or predict your outputs based on a set of inputs. So I was hoping it would be able to solve, but it seems like my GPU is running a little bit slower today. But yes, that type of workflow is something that is core to nTop and what we're able to do. I see a question from Vadim about does nTop geometry kernel operate with voxels? So nTop has our own geometry kernel, actually. So we developed something called Sequoia. That's our implicit modeling kernel. We also do use Parasolid. So when you import BREP CAD geometry, we use Parasolid to interpret those edges and faces. But then there is certain aspects of our geometry that are voxelized. So for example, our flow analysis uses voxels to define the flow domain. But the actual geometry does not use voxels. As far as I know, I might be wrong there, but I'm fairly certain that the rendering happens in a different way, and we have different options for rendering. So I'll just quickly mention here that our flow analysis solved, you can see the flow lines, which are pretty neat. And just to highlight the power of nTop, well, my flow analysis obviously is going to stay behind, but being able to adjust this angle and see the gyroid lattice in the center be so robust is again something that no other CAD system can really do. But sorry, to mention rendering, you'll notice on the trailing edge here, you see some of that kind of stepping. That is just an artifact of rendering. That is not in the actual geometry itself. So if I bump up my rendering option to adaptive rendering, then we should see a much smoother wing, and depending on how zoomed into the geometry I am, it'll be variable and will adapt to my viewing area to be smoother, but that is not part of our rendering technology. Cool. Yep, Radim?
Yeah, Matthew, I have a question regarding the surrogate modeling. So you mentioned that you use machine learning approach. Am I correct that the whole machine learning approach is about defining the surrogate model and then use it in optimization process?
Yes, that is the idea. You could use the surrogate model both for accelerated evaluation. So rather than running your full CFD, your surrogate model can predict the outcomes. But more typically, that surrogate model can be used for inverse design. So you can run your optimization script with that trained neural network to tell you, given these requirements, this is the optimal input parameters for your design.
Yeah, great. I ask this because this is the topic of my research, actually. The next question would be, do you support the ways to reuse these surrogate models somewhere else? Maybe in Python, maybe in some other software?
Yeah, so oftentimes the surrogate model will be trained in Python, for example, and then you can use it and integrate it back into nTop. But we don't currently have the full training built into nTop. What we're really good at is generating data to train a surrogate model because of our robust geometry, because of our analysis capabilities. But we don't yet have the full kind of surrogate model trainer built into nTop. So you would generate the data from nTop, then train your neural network in Python. Then you could actually plug it back into nTop. We have something called a run command block. So you can execute a Python script from within an nTop notebook. So it could be part of your kind of workflow. But that's all about how you plug it back in.
Okay, thank you. And yeah, so just to mention that I think that what we are doing right now in Splunk Cloud is making the kind of life cycle management for surrogate models. So I think we can discuss this in a separate call. I think this would be a nice idea to support, like blending nTop and Splunk Cloud. But yeah, this is a different story.
Yeah, that sounds great. Awesome. Well, I'll quickly mention again, you could go to ntop.com/education, request a free license, and please feel free to reach out. I'm here to help. And yeah, I would love to explore opportunities to do a hackathon or workshop with students in the fall semester or anything else to help you guys get started.
It will be a good chance for our students to familiarize better with your product.
Great. Cool. Well, yeah, thanks again. And let me know how I can help.
I guess we have a few meetings and then we'll may discuss in next steps how to
Great.
collaborate and obtain extra knowledges about nTop, because it's
Sounds
a
good.
real amazing product, and it's really simplify work. And it was a question how many time you may save, and comparatively it's in a really huge amount of time. But
Yep.
what I would like to mention in all these things, you must know the area of your scientific searches, yeah, because you may simplify it. You would like to simplify by this tool, but it may lead to the wrong way. Yeah? So you must know what you should to obtain. So be very careful with it. But nTop, it's a powerful tool, and you must have rules how to use it and obtain an opportunity for your
Yeah.
searches.
Great.
Okay, I guess we haven't any other questions. Many thanks to you that you find such opportunity to share your knowledge, to share a result of your products that could be used in wide sphere, starting from the thermodynamic and strengths and aerodynamic. It's a brilliant thing, and
Yeah.
I wish you good luck with an nTop product evolution. I think you have all these things, and we will be glad to use it for our study process.
Awesome. I'm glad to hear it. And thanks for inviting me. And yeah, looking forward to next steps.
Yeah, thank you. Thank you very much.
Thank you.
Have a good night.